Hi, welcome back to my channel. Today I want to take a look at loci in the complex plane and in particular perpendicular bisectors. Okay, so first of all, what is a perpendicular bisector? Well, you can see this black line on my screen between 2 points, Z1 and Z2. Right, if I show you the line joining Z1 and Z2, that green line, you can see the perpendicular bisector is always in the center. It's equidistant from Z1 and Z2 and it's perpendicular to the green line. Right, so the black line is 90 degrees to the green line and it splits Z1 and the line between Z1 and Z2 exactly in half. That's what a bisector means. Split the line in half, and perpendicular means 90 degrees. So that's good. I had fun programming this to make it work for any 2 points I choose. All right, lovely. So that's quite good. So that's what a perpendicular bisector is. So how does that relate to the complex plane? Well, I'm going to explain that on another little chart I've done. First of all, this is the form up there. This is the form of a loci in the complex plane, in this case a perpendicular bisector. The equation takes this form, okay, we've got z minus z1 equals z minus z2. These are magnitudes, so it's the magnitude of the vector z minus z1 and the magnitude of the vector z minus z2. What exactly does this mean? Well, I think it makes a lot more sense to look at it graphically. So on here, I've got 3 position vectors. Z1 and Z2, they are 2 fixed points that I've chosen, but Z could be anywhere. Right? Z's the variable complex number, okay? But Z1 and Z2 are fixed. Now you'll see this in a minute when I get through this explanation a bit. Now, Z minus Z1, we've got these 2 position vectors. What does that mean? It basically means if I'm traveling from Z1 to Z, so if I put a vector up there, hang on, let me just fill that in. Right, that dashed line represents Z minus Z1. How? Well, if I go minus Z1 would take me down Z1 back to the origin, because it's a position vector, plus Z would take me all the way up Z. And if I just rearrange that as Z minus Z1, I end up with this vector here going from Z1 to Z. Alright, that's a complex vector. Remember, this axis is imaginary and the x-axis is the real axis. Okay, so that's good. Now what about this other side then? I've got Z minus Z2. Well, following similar logic, if I go minus Z2, if I start at Z2, minus Z2 takes me to the origin, plus Z takes me to there. So I end up with a vector going from Z2 to Z. So let me just fill that line in. There you go. Now these 2 straight lines here mean the magnitude. So the magnitude of this vector here, Z minus Z1, is some size, right? We can calculate that with a bit of Pythagoras. And the magnitude of this line here, Z minus Z2, well, it says both them sizes need to be equal. So the magnitude of that vector must equal that vector. And in this case it does. You can see it's 1 diagonal square and 1 diagonal square. Now this is the point about Z being variable. Where could Z go where these 2 magnitudes will remain the same? Well, hopefully you can see it can only be anywhere on this line, right? Z is constrained under these conditions here, that it can only be on this line. That means the magnitude of this vector must equal the magnitude of that vector, and that will occur any time Z, this position vector Z, is on this perpendicular bisector. Okay, so that satisfies the requirements for this. Now, let's see what this might look like in a question. Instead of putting Z1, let's swap Z1. I can see there I've got, as a complex number, Z1 is going to be 2 plus 1i. right? The real part is 2, the imaginary part is 1i, or just I. So that's 2 plus I. And I've put that there, so instead of Z1, I'm having 2 plus I. So that's good. The next bit I need to look at is Z2. Well, Z2, the real part is 4 on the x-axis, and the imaginary part is same again, it's I. So this is Z minus 4 plus I in brackets, remember. Now, I've written the same thing again down here, just I've expanded the brackets, I've multiplied through by the negative, and that's what I get there. And this form is exactly what you're seeing here. This is what you'll see in an exam question. You might get given that, and you might have to draw the perpendicular bisector. So what would you do is go in reverse. You'd put that back in brackets, find your 2 points, and then it's quite a simple case of drawing the perpendicular. You can do it visually. You can see the perpendicular bisector visually. Okay, so that's I hope that explains that a bit. Now hopefully you can see Z can be anywhere on that line, and these 2 magnitudes will always be equal. The last bit worth noting is you're going to often get inequalities. So this will be loci in the complex plane, but now inequalities. You might have to shade the region. Now shade the region where the magnitude of Z minus Z1 is greater than the magnitude of Z minus Z2. So that means the magnitude of this vector here is larger than the magnitude of that one there. Well, if we made this bigger, it would force that point over into this region here. Okay, so again, I'm trying to give you like a more intuitive idea of what that means. So yeah, Z minus Z1 is greater than Z minus Z2. So this magnitude of this part is greater than the magnitude of that part. That would force my Z minus Z1 over into this region. And this anywhere in this region would satisfy this inequality. Now another thing you could do is just to check that. You could choose any point on the complex plane in this region. So choose this point, substitute your values for Z in, and then find the magnitude. So if I chose the point 4 plus 2i, I substitute that in there, 4 plus 2i, 4 plus 2i. This stays the same and this stays the same. I add the similar parts, I find the magnitude using Pythagoras, and I just check that the magnitude of this side is greater than the magnitude of that side. And that means I know I'll have the answer correct. Okay, so that's it. Short one. I hope that gives you a bit of intuition and more of a visual idea on loci in the complex plane, or perpendicular bisector loci in this case.